Hello, welcome everybody. Welcome to the second part of the first lecture of week 3. And in this lecture, we're going to talk about statistical independence, which is an important quantity in the computation of intersections. If the events are independent, we'll see shortly that that means I can just multiply the probabilities and I don't have to worry about these conditional probabilities, which are typically not easy to estimate. Okay, so we say that events A and B are independent if the occurrence of one does not affect the probability of occurrence of the other. In other words, if the probability of A given B is just the original probability of A, then A and B are independent. And if they are independent, it also means probability of B given A is just equal to the original probability of B. Note that this simplifies the probabilities of intersections, as I mentioned. Probability of A intersection B, we know our rule is probability of A given B times the probability of B. But now, since probability of A times, given B is just my original probability of A, this probability of an intersection becomes just the product of the two probabilities. So whenever you see an intersection, ask, are the events independent? If they are, things are much simpler. I just multiply probabilities. So for example, if we have probability of A intersection B intersection C, this would normally be written as probability of A given this thing times the probability of this thing. And the probability of this thing is probability of B given this thing. So this thing, the probability of the intersection of three things, turns into the product of three things. So one multiplication for each intersection. But the first one is the probability of A given B and C. So this is a more complicated conditional probability. The second one is probability of B given C. And the third one is probability of C. And of course, this can be done in any order. So you could also write this as the probability here is the probability of C given A and B times the probability of A given B times the probability of B, and so on and so forth. These are all equivalent. If A, B, and C are independent, however, then each of these things, probability of A becomes independent of whether B and C occur, so this becomes just the probability of A. And this probability of B is independent of whether C occurs, becomes just the probability of B. And this is the probability of C, so probability of A intersection B intersection C is just probability of A times probability of B times probability of C. Much simpler. So for unions, just to recall, we like it when events are disjoint. Probability of A union B union C would normally be composed of 7 terms, but if they're disjoint, it's just the sum of 3 terms. If and if they're independent, then probably their intersection is just the product of the 3 probabilities. So independence we like for intersections, disjointedness we like for unions. I should also point out that if events are disjoint, they cannot be independent, and vice versa. If they're independent, they cannot be disjoint. So the two things are essentially opposites. In the English language, independence often seems to mean that they're separate. And so often we get confused, or we think of independence as meaning the same thing as disjointedness, but in probability theory, they are almost opposites. I say almost because independence is actually a much stronger statement than disjoint. So bear that in mind. They're completely different. If it's independent, it helps us with intersections. If it's disjoint, it helps us with unions. So we can see this. If A and B are disjoint, then their Venn diagram looks like this. There's no overlap. If A occurs, B cannot occur. Well, if A occurs, if we know that B has occurred, then the probability of A drops to 0. And this is not equal to the original probability of A. So we can see if they're disjoint, they are highly dependent. The occurrence of B makes a big difference to the probability of A occurring. If A and B are independent, then the intersection between A and B must exist and must be precisely equal to probability of A times the probability of B. So independence is a much more strong statement. It's not just that they're disjoint, or not just that they're separate circles, but that they overlap, and they overlap by a precise amount. If they don't overlap by that precise amount, then they're no longer independent. So if this area here is not quite equal to probability of A times probability of B, even though there's still an overlap, they're not independent. Okay. So let's look at some examples to illustrate this. Suppose a random sample of size 2 is to be selected from a lot of 100 parts, and it is known that 98% of the parts are good. Let's let A be the event that item 1 is good and B the event that item 2 is good. What is the probability that both items are good? If the first item is replaced before the second is selected, what now is the probability that the two items are good? Let's look at the first one first, and let's assume that we keep the first item. So if that's the case, then the event B depends on A, because once A has occurred, we've changed the lot size and perhaps the number of defectives. So we're looking for probability that both items are good, A and B. And we can write that as the probability that the second is good, given that the first is good, times the probability that the first is good. Well, the probability that the first is good is 98 over 100. There's 98% of 98 of the parts are good out of the 100. If then we multiply that by the probability that B is good, given that the first was good. Well, if the first was good, then we've reduced the number of good ones by 1, and we've reduced the whole sample size by 1. So the probability of B given A is that there's now 97 good parts out of the 99. Multiply these two probabilities, we get 0.9602. Now we look at what happens if we replace the first part. In this case, because we replace the first part, the second draw has nothing to do with the first one. They're independent. Okay, the probabilities remain unchanged. In fact, each draw probability of good is 98 over 100. So we get 98 over 100 times 98 over 100, 0.9604. And basically there's really not much difference between these two numbers. And that's typically true if the number sampled is less than about 10% of the lot size. So often we can assume independence if we're not sampling very many out of the total loss, which is to say we can ignore the fact that we replace or don't replace. We assume replacement so that they become independent, and we get pretty much the same results. Okay, let's look at another example. Let's suppose we have 4 machines, A, B, C, and D, that are running independently. If their probabilities of failure are probability of A is 0.01, B 0.008, C 0.005, and D 0.015, what is the probability that none of them will fail? The key word here is that the machines are running independently. So we see that there. That means, and we're looking for probability that none of them will fail. Let's see, A is probably a failure, so we're looking for the probability that A complement and a B complement and C complement and D complement. So that's an intersection, and we're told that they're independent, so that intersection simplifies. So let's define A as the event that machine A fails, B event machine B fails, C machine C fails, and similar for D. Then the probabilities of these events are given up at the top here. Now we want to find the probability that the first one doesn't fail, and the second one doesn't fail, and the third doesn't fail, and the fourth doesn't fail. This is ands or intersections. Since they're independent, it's just a product of the 4 probabilities. And each of those probabilities is 1 minus the probabilities up here, since they're complements. And so I just plug in the numbers and multiply them out. I get 0.9625. Okay, another example. A machine produces defective items with probability P, and are therefore non-defective with probability 1 minus P, which we will often call Q, and we'll see that later in this course. If 6 items are selected at random and tested, what is the probability that exactly 2 are defective? So I'm selecting items coming off of this machine, and I'm looking at the first 6 that I select. What is the probability that exactly 2 of those are defective? And let's assume that items come out independently. So whether item 1 is defective doesn't make any difference to the probability of item 2 being defective, and so on and so forth. So let's let DI be the event that the ith item is defective, and so DI complement is the event that the ith item is non-defective. What are we looking for? We're looking for probably that 2 out of the 6 items are defective. Okay, so we can do this. We'll look at a specific case here. Let's look at the probability that items 1 and 2 are defective and the others are non-defective. So that's the probability that I got D1 and D2, and all intersected with all the rest being non-defective. And I know that since they're independent, this is just the product of the 6 probabilities. The probability of this one is P, this one is P, and the probability of all the others being non-defective is Q, 1 minus P. So I got P squared Q to the 4th. However, that's not the only way I can get two defectives out of the 6. It could be that items 2 and 3 were defective, or items 3 and 6. So I basically have to look at all the possibilities here. And they all have exactly the same probability of occurrence. They all involve 2 defectives and 4 non-defectives, so they all have probability p squared q to 4th. So all I really need to know is how many ways can I choose 2 defectives from the 6 without regard to order. And this is a combination. The number of possible combinations of 2 defectives of 6 is 6 choose 2. So the probability of 2 defectives is just 6 choose 2 p squared q to the 4th. And that concludes this lecture. Thank you for listening.